It looks like I've got several of you in here. Thanks for coming. Again, I want to point out that this is this is a internet class where we actually have a scheduled meeting time, obviously on Tuesdays and Thursdays, 5:30 to 7:40 p.m. So I do expect you to attend, but if you have to miss, it's not that terrible of a deal because you can actually view the video of the meetings because I post them on my YouTube channel afterwards. So don't worry too bad. I do keep roll just to keep track of that, and because that's the sort of thing we're supposed to do as teachers to keep track, make sure people are progressing, so on and so forth. So what I normally ask my students to do when they get in is go ahead and chat me your first and last name, and that's what I use as the role for each day. So I can always just check back and look at the chat, and I'll see, oh, okay, such and such student was here, but other students weren't. So if everyone could go ahead and chat me your first and last name, I'll try to remember to ask everybody to do that again later in case they hadn't already done it. Uh, I am Mr. Younger. I will be teaching your Physics 241 course this semester. We are using Giancolli's fifth edition of Physics for Scientists and Engineers with Modern Physics. The book is actually written for a three-semester sequence, but TCC only offers the first two semesters. However, a lot of places you might go to, UVA, Virginia Tech, ODU, they often do offer three semesters. And the way we try to accommodate that to help you guys is we normally, not in the summer semesters, because we're so pressed for time, we usually don't have the time in the summer semesters. But normally in the regular semester, we try in Physics 241 to include chapters 1 through 11 and then 14 and 15. And then if we have time, we go ahead and cover special relativity, which I believe is chapter 35 or 36, something like that. I think it's 35. Then in 242, we go and cover chapters 17 through 31. And if we have the time, then we jump on to chapter 36, 37, 38, which are quantum mechanics, and then maybe even to a later chapter on nuclear physics. And if we have even more time, we cover particle physics. So the good news is that if you're taking this in the regular semester, you might get to experience some of those, and therefore you'll be a little bit better prepared if you go somewhere where you need the third semester. The bad news is that during the summer, we're not going to be able to do that more than likely. But again, some other good news is that I do offer those chapters as extra credit homework assignments. So you can still do the chapter on special relativity this semester. And you can't really do that very well without at least sort of reading over the chapter, looking at the examples, and then trying to solve the physics problems for the homework. But I will count that as extra credit, and you'll have some experience with relativity. And similarly, you could do that in the 242 course with quantum mechanics, nuclear physics, particle physics, cosmology, all that good stuff. So I'm not going to do too much to talk about the syllabus. I've talked about it. You can find introductions to my syllabus on my YouTube channel. But the main thing is I'm going to make a separate video that I'll just post that covers the syllabus because it's actually the same for all of my classes. All of my 241 and 242 classes have more or less the same syllabus. The most important thing that I need to make sure you guys know is that each chapter will have at least two homework sets. There'll be a homework set that's just called homework, and that's where you solve physics problems. And then there's a homework set called conceptual homework, and that's where you're asked conceptual questions. And I use that as pretty much the only time I get to cover very many concepts, meaning I'm not going to take separate time to talk about the individual concepts except where I need to so that you can solve physics problems. So all of your understanding of the concepts are going to come from you reading the book and doing those conceptual questions. So make sure you take them seriously. However, sometimes a given chapter will have two sets of problems or even three sets of problems to be solved. So you have at least two sets of homework for every chapter we cover. In addition to that, I have online tests. They're worth about the same as the problem homework. So the in your grade system, 5% of your course grade is your conceptual homework grade, 10% is your problem solving homework grade, and then another 10% is your online test average. I do drop the lowest online test. I drop the lowest I drop the lowest homework problem set as well, and I didn't put it in the syllabus, but I usually drop the lowest conceptual as well. It's just I'm not required to, so I don't put it on the syllabus so that I'm not required to. I might not do it, I might, but I really want you guys to take the concepts seriously so you can learn them a little better. If I had my ruthers, I would do it like I did at Chapel Hill, and like they do at MIT and places like that, where basically I can teach for 3 hours a week. That's the requirement for this course is 3 hours of lecture and then 3 hours of lab. But what I would do then is offer another 2 or 3 hours a week for what we call recitation. And then in the teaching session, I would do a lot of demonstrations that show concepts and stuff like that. And then at recitation, I would reserve that for problem solving and maybe solve a few problems in the main lecture as well. But when I've done that, and I've done that a lot in the past, it turns out nobody shows up. The only people that show up for recitation because they're not required, and I can't make them come. It's actually illegal for me to do that. But when I did offer that as an extra thing, pretty much the students that were really going to get an A anyways, they showed up religiously and did all their work and had great questions and stuff like that. And a couple people would show up late in the semester when they realized they were about to fail. But other than that, I'd get literally out of a class of, let's say, 50 students. I would normally at Chapel Hill, I would normally get about 35 students showing up. Whereas when I had a class of, say, 24 students here or at another community college, out of 24, I'd get one or two. So it's just not useful. But that's the way I'd rather do it. And you can by all means check out other lectures online. For instance, MIT has Open Courseware (OCW), and they have the equivalent of these courses. And those are some of the links that I offer you in helpful documents and links, so that you can watch and learn more of the concepts and see some of the fun demonstrations that some of those famous teachers use and do. So by all means, do that. Just so you'll know, I'm going to chat out my YouTube channel. It's on the syllabus, so you probably already saw it, but just in case you didn't, it's www.youtube.com/at physicssolutions.com. Notice the P, the S, the D, and the T are the D and the C are capitalized. That's my YouTube channel. And the first thing I need to tell you guys is every week or every day that I do this, this video will be edited very minorly at the end and then posted on my YouTube channel. Usually the same night, but sometimes the next day. And that's really the case in the summer because these videos go for 2 hours and 10 minutes, and that takes a lot of editing and it takes too much time, so I usually can't get it posted the same night, but it should be up by tomorrow. For instance, it'll be there. And the important thing about me telling you that is I got to let everybody know, hey, whenever I do a Zoom meeting, I put it on my YouTube channel. So if you're a person that doesn't want your name or your face or your first and last name to appear on the internet, you got to do a couple things. One, you have to change your Zoom account name to something other than your name. You could change, for instance, if your name was Billy Younger, like mine is, you might just change it to B Young or something like that, or Billy Y or something like that. That way, if someone sees it on the internet, they won't recognize you. Two, you want to make sure you don't show your face and uh, unless I specifically need you to show your face, which I can't imagine I would, but you want to make sure you don't show your face. By the way, if I ever do a testing proctoring through Zoom, I would not put that on the internet, so you don't have to worry about that. But the third thing you have to do is you have to email me and tell me, hey, my name is such and such. I'm in physics 241 section D01B or whatever section you're in, and I cannot have my face or name put on the internet. And then when you let me know that, then I'll make sure I do my due diligence to remove any sightings of your name on the videos and stuff like that before I post them. So make sure you do that. Make sure if you have any friends in the class that you let them know that that's it in case they don't see this part. I think I did put it in my, I know I put it in my syllabus, and I want to make sure everybody knows that, but I just don't want to harm anybody. I mean, there's literally people that are, on the run from, abusive wives or abusive husbands or the mob or stuff like like that. I literally had a friend in grad school who was running, quote unquote, from the mob, and I won't tell you the mob from what state or anything like that, but specifically the parents had gotten into quite a bit of heck. And for that reason, she couldn't be on the internet or anything. So that's what I'm looking out for. I don't want anybody to be put in danger because I'm, putting my videos online to help people. So in addition to that, I want to let you know that one of the things that's important about the syllabus that, again, I'm not covering all of the syllabus. I'm trying to hit a few very important parts, is that when you email me, you should expect me to reply to you within one business day. The way that works is like a Monday or a Tuesday or a Wednesday or a Thursday. If you email me as early as 12:01 a.m. on Monday, then I have to reply to you no later than no later than 11:59 p.m. on Tuesday. I don't know why the number one kept popping up. I guess because I was seeing the digits instead of thinking of the number. So again, on a regular day of the week, Monday, Tuesday, Wednesday, or Thursday, if you send me an email as early as 12:01 a.m. or even 12:00 and 2 seconds a.m. on Monday, then I have to reply to you by 11:59 and 59 seconds on Tuesday p.m. Okay, so that's the way we rate what one day or a turnaround is on an email. If it happens to be a Friday, for instance, and you email me as early as 12:00.01 seconds. Okay. If you email me that early on a Friday, then I have to reply to you by no later than 11:59 and 59 seconds on Thursday, I mean on Monday. So that's how it goes over the weekends. Now, if in the event that you send me an email and you don't get that response from me and you haven't had another email that I sent out to everybody or an announcement that I made to everybody that answered your question, because that's sometimes how I reply instead of actually replying to you person by person. If I get several people that send me an email about the same topic, I'll write one email or one announcement and I post it, and that covers everybody. So that might be what happened. But still, if you feel like you didn't get your question answered, that's a very good time once one business day has passed and you haven't gotten the response and you still need the response, then I recommend that you send me a text message. Don't worry about what time of day it is. I've got it set up where if I'm in bed, then it's not going to wake me up, so you're not going to bother me that way. I also don't want my personal cell phone out on the web, so I'm going to type it here in the chat. And it's on your syllabus too, so you don't have to only get it from here. But just in case you haven't seen the syllabus yet, that is my personal cell phone number. And what you need to do is send me a text message that way. Don't try to call me first. I don't answer phone numbers I don't recognize, and obviously you guys aren't in my contacts, so I don't recognize you. And I'm sure you know why, because you're probably getting spam mails, phone calls all the time. So I don't answer that, but you can text me. But when you do text me, you got to let me know your first and last name and what class you're in. For instance, this is PHY 241 online, or this one might be what I call night. Yeah, this is the one I call night, 241 night. So you need to give me your first name, your last name, and the fact that you're in PHY 241 night whenever you text me and every time you text me, because unless I kept all those emails, and even if I did, it's still a pain in the butt. But unless I kept all those text messages, uh, then I won't be able to just look at the text and see who you are from your previous one, and I won't necessarily remember your number. That being said, I normally do keep them, but it's a real pain because a lot of students, I'll have, 30 text messages with them, and when they write and ask a question, if I don't recognize that number, I have to scroll through all those 30 texts to find your name. Uh, so one more rule in addition to these, and this one's about the email as well. And I say this on the syllabus, and I tell you in the cut and paste section of your syllabus that you're supposed to turn in to me by June 1. I tell you that when you do email me, you have to do some very specific things. One is you have to email me only from your TCC Gmail account. Okay. That is when you go into SIS to log into Canvas, for instance, you'll see there's a place where it says Gmail. That's where you can access your TCC email account, and it is a Gmail account. But that's the email you should use when contacting me. Do not, even though Canvas allows it, do not send me an email through Canvas. Okay. So you send the email through TCC's Gmail, through your TCC Gmail account. That's the first thing you do. The second thing you do is you start the subject line of any email with the name of this course specifically, and I wrote this on the syllabus, and again, that's why I think I remember it was PHY 241 space night. Okay, I'm pretty sure that's what I told you, but that's what you should put as a subject line, and that also means even if you're replying to an email from me, that means you got to go in the subject line of that reply, click to the left of the RE that they automatically put there, and then type in PHY 241 space night. Okay, if you don't do that, there's a high probability that I will never see that email. The third thing you do is the same thing you had to do with your text. You got to tell me your first and last name. Okay, so every time you email me, tell me your first and last name. Since you have PHY 241 night in the subject line, then I know what class you're in. And since you're using your TCC email account, I know you really are from my class. So that's the big thing you got to do. Now, as I have said to you guys, the chapters we plan on covering are chapters 1 through 11 and then 14 and 15. Any chapters outside of that will automatically be considered extra credit. Even if they don't have EC next to the name, even if they don't have the word extra credit in the name, if they're outside of chapters 1 through 11, 14, and 15, then they're automatically going to be extra credit. The way my extra credit works, by the way, is it just replaces, when I give you homework extra credit, it replaces one of your grades that aren't 100 with this grade. And the way extra credit works is if you do it right, I give you 100. If you do it more or less mostly right, I basically look at it and I use roughly a 75 to 80% correctness rule. And if you get somewhere between a 75 and 80 or higher, then I'll automatically give you full credit and you get 100 for that. So that 100 is going to automatically replace one of your lower grades. And if you don't do it at all, you get a 0, but that's okay because I up the number of dropped homework grades by 1 for each of the online extra credit, or for each of the extra credit assignments I give you guys. Now, that being said, I don't do that till the end of the semester, so your grade's going to constantly look worse than it will be as a result of those low homework grades, and that's just fine. The final thing I want to talk about that's sort of syllabus talk as well is I don't want you trying real hard to get perfect scores on your homework. I get it. You're an A student. You're used to making A's and you want to make A's. I applaud that. I want you to make A's as well. But it turns out that every homework system online has errors in it. And Pearson's one of the better ones. Norton and Pearson both are really good publishers and do some good stuff. Cengage is pretty good. Not as good as Norton or Pearson, but in my opinion. But Pearson does a pretty good job. But the fact of the matter is there's always some errors in there. And in order for you to get 100, sometimes it would literally force you to do something that's inconsistent with the way you're supposed to solve physics problems. So instead of you focusing on that, what I want you guys to do is use the homework as what it was meant to be. The homeworks are meant to be your chance to make sure you really understand the material and that you can solve physics problems. So it's basically you go from the examples that I cover in class, the examples that you read in the chapter, and that should be enough to get you started on figuring out how to solve the homework problems. Uh, you should shoot for a grade around the 80 mark. If you get, 78 is probably about the lowest I'd want you to make. And you can make higher, but don't really force yourself or don't spend extra time to try to make sure your grade's above an 80. Just make sure you solve all of the problems and you solve them. Okay. If you get them wrong, I don't care. Just learn what you did wrong so that you won't do it wrong again. I know that's going to set you up in some way to think, oh crap, if I do that, then my homework grade's going to only be an 80. It's going to bring my grade down from an A to a B. And that in some sense is right, but I've got two mechanisms going on here. One is that I've got this copious amount of extra credit assignments that replace all those 80s or lower with hundreds. So you've got a chance to bring it up to 100 anyways just by doing the extra credit. And two, I promise you guys that a couple weeks before the end of the semester, I will come to you and tell everybody, okay, here's what we're going to do, and this is what you're going to do. And it will actually have the chance of erasing all the negativity of your homework grade. In other words, I have a way for you to really bring up your homework grade or your grade that's being negatively affected by homework. So you just got to trust me on that. And if you look at my student reviews, you'll find, I'm sure I haven't looked at them in years, but I'm sure you'll find some people complain about me, but most of the times I think you'll find that people say I'm difficult to get a really good score in, but I work really hard and I'm helpful and I try to help you. And that's what I'm going to do. I'm going to try to get you the best grade that you can deserve. Okay. So just don't fret it too much on the homework. Use it for what it's for. It's not a chance for you to bring your grade up. It is a chance for you to learn how to solve physics problems so that you can make good grades on the stuff that matters. 10% of your course grade is not that big a deal. Uh, but if you combine that with the online test, you're now looking at 20% and it's starting to get a big deal. And then you look at the face-to-face tests, which are like 25% or 30%, I think. Uh, with those, that's another chance. But you can't do those unless you use the physics homework problems to learn how to solve physics problems. Okay. I am no longer offering online, or excuse me, face-to-face tests that are completely multiple choice. There are also going to be fewer problems. It's usually going to be now probably 2 to 5 physics problems that you solve and maybe 1 or 2 conceptual questions on your test. And none of them are going to be, normally are not going to be multiple choice. They're almost all where you're going to have to work out the problems, start with the equation that's important, fill in the numbers with their units into that equation, and then solve that equation using calculus or algebra to get the variable you need, and then plug that into something else, and so on and so forth to solve the problem. So that's really the gold standard here is your ability to solve physics problems on your own. Be careful. Don't lean too much on the resources. For instance, my online tests are completely online, and you're allowed to use open book, open notes, open any book, open anybody else's notes as well, and even open Google searches. So you can literally do a Google search for the specific question that you're running into on the online test. And a lot of times that question will come back with an answer, and a lot of times that answer is the right one, so you can go ahead and write down the answer. But the more important thing is for you to figure out, can I get that answer so that you know how to solve the physics problem. I don't mind at all, and I'm telling you, it's not cheating to do this. Okay, you're completely allowed to do that, and that's how you can bring this grade up. But the big thing is you're cheating yourself if you're not also learning how to solve those problems and get those answers. Okay. So keep that in mind. There's a lot to be said for the more you use those resources, the less are the less likely you are to get the chance to fully learn from it. It turns out that if you sit and watch me solve 100 physics problems and you pay close attention, let's say you just pay complete attention, you're enthralled by it, you think I'm the most interesting instructor in the world, and you think I'm so helpful that you completely understand everything. Even if that really was all the truth, if you watch me solve 100 physics problems, it's probably not as valuable as you solving, let's say, 10 problems on your own. Okay, that's a reality of math and physics and probably chemistry to some extent. I'm assuming there's some levels of biology and other sciences that are like that, but I know for a fact from my own experiences in chemistry, engineering, and physics and math that that's definitely the case. So keep that in mind. Now, does anybody have any questions before we get started on chapter one? Okay. I've mentioned to everybody, some more people have come in since then. Asked everybody to chat me your first and last name. That's what I do for roll. Normally, you can do that right before the end of class, but I don't really mind if you do it at the beginning of class because honestly, if you come in and then sign into the roll and then leave immediately, you're only harming yourself. So I don't want you to harm yourself, but I'm saying it's going to pay off in the end. So I would recommend against doing that, but you're welcome to. Okay, it's just not not going to help you. All right, so let's go back to now chapter one. Chapter one is called Introduction, Measurement, and Estimating. And when you open up that section, you'll see, or that chapter, you'll see the subsections in it are 1-1, how science works, 1-2, models, theories, and laws, 1-3, measurement and uncertainty, significant figures. That topic, actually, the first two topics, how science works, models, theories, and laws. I'm going to give you a brief introduction to my thoughts on this, but to be honest with you, when you start doing the practice tests, the homeworks, and then ultimately the face-to-face tests, you're going to be using questions, answering questions from the bank that the author created. That's part of the advantage of taking the practice test that I recommend you take. Not only do you get potentially 5 points added to your final exam grade, but you're getting to see every time you do one of those practice tests, you're getting to see a new set of problems that come from the bank of problems that I use to make the actual test. So I guarantee my students, for instance, that 80% of the points, as a bare minimum, 80% of the points on a actual test come from questions that were in that bank. That being said, I think I've gotten as low as maybe 95% coming from that. In other words, I very rarely even use questions that don't come from the bank. It's almost always 100%, but I guarantee you at least 80%. So that's all another reason to do the practice test to begin with. But not only that, you also get 5 points that could be added to your final exam grade, which is really a hard thing. And 5 points is a big gift to you guys. So, anyways, make sure you do that. As I was saying, because of those practice tests being made of the author's banks of questions, then what I want you to do when you're doing those online tests and online homeworks is think in terms of what you learned from the author. So I will give you my ideas about models, theories, hypotheses, and laws and stuff like that, but they're going to be a little bit different from what you hear from the author. So when you go to answer a question, you need to think about what the author said, not what about what I said. Even though they're at some higher level, they're equivalent, just not exactly the same. So stick to your reading, at least for sections 1-1. Well, I mean, you should be reading the whole book, period. But I know a lot of students don't. And what I'm telling you here is I'm not covering section 1-1, section 1-2, or section 1-3 in a way in lecture that will be sufficient for you to follow and do well on the practice test and the test. So you really need to make sure you definitely read those three subsections as a bare minimum. 1-4 is on units, standards, and the SI system. Unit 5 is on converting units. Unit 6 is on order of magnitude, rapid estimating. And 1-7 is dimensions and dimensional analysis. I will be talking about units, standards, the SI system. I will be converting units. Probably next class, I'll talk to about order of magnitude and rapid estimations calculations. But I also plan on tonight working on section 1-7, which is an asterisk subsection, but this is one where I definitely cover it because dimensional and what I also call unit analysis is extremely important, and it's sort of the first foot in the door for you to figure out how to come up with a hypothesis for a theory. Sometimes it's just a matter of saying, hey, I see this phenomena and here's this important variable, say velocity or something, and I think that velocity depends on these quantities, mass, uh, initial velocity, and force. And you might not have any physical understanding of anything, but immediately using unit or dimensional analysis, you can automatically conjure up an equation for that velocity based on velocity, mass, and force, for instance, just by doing units. So that's why I consider it extremely important, and you'll see some robust examples. Okay. So every chapter starts off with a chapter opening question, sometimes two of them. I want you to make sure you always, always, always do that before you go on reading any further in the chapter. So every time we start a new chapter, you should go over the chapter opening question and guess at it or ideally use as much logic as you have and as much knowledge as you had to come up with the best estimate of the right answer, and then wait as the book goes on. Keep an eye out for it answering that question or those questions for you. So make sure you do that. That's the scientific method being enacted in real life on the subject of learning material. So it's really a good way of making sure the stuff that you learn stays in your head. Now that we have that, we're going to go ahead on and I'm going to talk about the other topics. So your book talks about how science works. I'm going to give you a quick little picture, and this is where I'm deviating a little bit from what the author said. So this is a part where I want you to understand it because it gives you a deeper understanding of how science is conducted day in and day out, a more realistic one than that, little list of scientific method steps that you learned in grade school. But it's a little different from what the author says. So you want to pay close attention, as always, in your textbook and any textbook. Anything you see in bold print, you better assume that that is a definition you need to know, or that's a word whose definition you need to know. And that's the truth with physics as well. I'm not going to take the time and tell you, hey, you need to learn observation, theory, hypothesis, testing, predicting, that sort of stuff. I'm not going to tell you that. I'm not going to tell you that you need to memorize what the meaning of model is and stuff like that. But you should know as a college student that if you see something in bold print, then you certainly need to commit its definition to memory. If you see something called a law, or something that a whole subsection or a whole chapter is named after, that again is something that a college student should know. Hey, here's a whole chapter dedicated to this thing called such and such's law, or here's a whole section within a chapter named after such and such's law. That seems to me to make me think that's pretty important. So I'm going to go ahead and commit that to memory. So that is a fact too, and I'm not going to, repeat it every 2 weeks or every week or anything. So make sure you do that. For instance, in this course, you will cover Newton's first law of motion, Newton's second law of motion, Newton's third law of motion, Newton's law of gravity, Kepler's first law of motion, of planetary motion, Kepler's second law of planetary motion, Kepler's third law of planetary motion. You're going to learn conservation of linear momentum. You're going to learn conservation of angular momentum. All of those are big things that you should commit to memory. And as soon as we cover those are fair game for me just asking you what I think is a simple question is state Newton's second law of motion, or state Kepler's third law of planetary motion, or under what conditions is linear momentum conserved, that kind of thing. So be prepared to be asked that question on every test, okay? And in fact, when you get to the end of the 2 semester course, I will ask you all those facts as well about the first semester, as well as the new ones you learn in the second semester, which would include, for instance, Gauss's law, Ampere's law, Faraday's law, the ideal gas law, the Stefan Boltzmann law, Kirchhoff's laws, Kirchhoff's principles, all sorts of stuff like that. The first law of thermodynamics, the zeroth law of thermodynamics, the second law of thermodynamics, the third law of thermodynamics. All of those principles are things that by the end of 2 semesters you should have committed to memory in such a way that at the drop of a hat you could regurgitate them. Okay. All right, let me get off my soapbox. But as I was telling you about how science works, I'm going to go ahead and share my screen with you so that you can see what I'm writing. And hopefully I can do that in a second. It seems like, great. I made the document, but it just disappeared. Stop that. Taking forever. All right, so hold on a second. I will be there in a moment, I promise. Let's say this one. Okay, so today's the 19th. I got that. And this is physics 241 N01B. So I've got to make sure that is the case. Okay, so I've now got my notebook ready to roll. I just got to make a copy of it, and then I can open it up for you. So now I'm going to go ahead and click share, and I'm going to say share my iPhone, iPad via AirPlay, and it should pop up here any minute now. Okay, so this is a note-taking program I use called Good Notes, but there's the document that I want you to be able to look at. I've got the window open. I'm going to put this box over here to the right, and I'm going to open up the chat so you guys can still communicate with me via chat. But if you have any questions, feel free to just blurt out your question. You don't have to worry about interrupting me or anything. If it gets too onerous, then I'll just say, hey, can we hold the questions till the end? But I've never had to say that, so I'm sure it's going to be fine. So just keep on asking whenever you have a question. I definitely want you to, and be advised. I'm never going to hold it against you that you ask a question that you might think is stupid. One, I don't generally think of questions as stupid or not. Okay. I'm a teacher and I'm trying to teach you something that's scary and complicated for a lot of people. So it's certainly fine for you to have these questions. And if you have the question, you can be assured there's probably three or four other students in the class that have the same question. So please, please, please ask me questions as soon as you need them. So, uh,
Excuse me.
yes, sir. Go for it.
So, where do we go to access the notebook? Because I'm looking through Canvas. I might have probably looked over it, but
Okay. The notebook, like where I'm putting my notes in right now.
um, no, you mentioned like chapter one, chapter two. Where do we go to like see that?
Okay, gotcha. So when you go into Canvas, have you been to Canvas already? I assume you have because that's
Yes.
where this invitation is. But yeah, when you go to Canvas, if you look off to the left-hand side, there's a Access Pearson link, and you click on that, and at that point, they're going to ask you for your access code, which if you bought a new book, it automatically comes with it free. But if you don't have it, you're actually kind of lucky because you can buy it on the website for cheaper. It's actually the cheapest way you can get it is buying it through the website. So you can purchase it there if you have a credit card, and they'll give you like 1 year of access to the homework set as well as an electronic version of the book. If you want a hard copy or a printed copy, you can do that too, but you really, really, really don't need it. In fact, if you like to have a hard copy and you don't want to pay that much money because a hard copy, well, we were up to about $320 for this package at one point, but now we're back down to if you're buying it from the website, it's normally around $80 for the ebook plus the access to the homework for a whole year. So that's a lot cheaper. But if you really want a physical textbook, then I would say go online at eBay or Amazon and look for a used copy of the fourth edition or the third edition or even the second edition because the Giancoli, the text hasn't changed horribly much. The examples have changed a little bit and the problem sets have changed a lot, but really it's the same reading material. So if you really want a physical textbook to read, you don't like reading online, just get you a cheap version of an older edition. I've seen them sell for $2, $3, $5, stuff like that. But otherwise, just pay the 70 some dollars and let me know, by the way, what it is now. I think last semester it was like $79 for access, but that's where you get it. And then when you go into Canvas in the modules, after you've already signed up for My Lab and Mastering, you'll get the week one module and it'll have homework links. And there you click on them and they take you to the online homework assignments. Does that help, Zane?
Yes, it does. Thank you. Thank you.
No problem. It might not work for a little while just until you get your access code. But by the way, they do give you a free week, a free 2 week grace period. So there's no excuse for missing the first assignments. You got to have week one, chapter one has to be done by this coming Sunday. So make sure you get those. Oh, actually, since you guys are a Tuesday, Thursday class, they'll be due this coming Monday at 11:59 p.m. So everything I normally say about your homework being due at 11:59 p.m. on Sunday, for you guys, it's going to be 11:59 p.m. on Monday. So just every Monday, assume that 11:59 you have at least two homework assignments that are due. You might even have more because the way this course is set up, I've got to cover about 1.5 to 2 chapters every week. So you got to make sure you do those homeworks. And I'm not necessarily going to completely do all the examples in every chapter. I've given you the links to my YouTube channel where a ton of videos are on previous examples that I've worked out, and I'm trying to do the examples that are hardest. So when we get to whatever week we say chapter 5 is due, that Sunday chapter 5 will be due. Okay, or that Monday for you guys, chapter 5 will be due, no matter whether you felt like I finished chapter 5 or not. Okay. All right. So what we were talking about is how science is conducted, and I want to give you a little bit bigger of a widescreen photo of it. Uh, Science often begins with, though it doesn't have to, it begins often with an observation slash experiment slash test. In other words, every time you observe something, that is the laws of physics unfolding in front of your eyes. So, in some sense, that's still an experiment. It's just not an experiment that you actively set up to behave a certain way. So sometimes we just need to call it an observation because you didn't, put everything in an exact place. You didn't have any control of the constituents or anything like that. And then sometimes it is an actual experiment, but then other times it's just again either observing something happening and just testing to see if it happens the way that you expect it. So that's often what happens. And an example I use just to give you some idea of how minimal and non awesome it has to be. You could look at a toddler and you see a toddler like out in your front yard or something. They stiff arm their arm and they have a ball in it and they just sort of with a straight arm just let it go. And you look and you see the ball leave their hands and it makes this arc. And you might think to yourself, wow, it's almost like that ball left his hand and then followed through the arc of a quarter of a circle. So you might hypothesize that, hey, I bet the path followed by a ball released from a toddler's stiff arm is exactly the path of a quarter of a circle. And what you've done there is created sort of a model, i.e., a circle is the definition of the trajectory of a ball thrown by a toddler. Okay. And from that, you can also make predictions. You can say, okay, well, here's this other kid. This kid's like a foot shorter. So I suspect their radius of their sphere or circle is going to be 1 foot smaller. There you've made a prediction. That brings me up to here. Hypothesized. So we hypothesized slash made a model. Both of those can be part of the same thing. Sometimes it's just a hypothesis where you're just sort of making some statement. Sometimes it's a hypothesis that has a model accompanying it, and that's some physical thing or some model that you can see in your head that represents reality, even though it doesn't necessarily have to have anything to do with reality. There's no reason in the world to assume that a ball leaving a toddler's hand is going to trace out a perfect circle, but you did it because it looked like it might be, and that's a curious thing, and that's the good thing that humans have evolved to have is a amount of curiosity. So you use that, and at that point you are hypothesizing. Then what you're supposed to do is with that hypothesis you're supposed to make a prediction. So, as I said, you saw a second toddler come out, and that second toddler was a foot shorter. Therefore, when their arm was straight, it looked like the distance from the ball to the ground was 1 foot shorter than it was with the other child. Therefore, the radius of the circle should be 1 foot smaller. And then you watch it. So, what's happening here is you had an observation which caused you to make a hypothesis or a model. Since I put a D on there, I called it modeled instead of model. And if I would have said hypothesize, I would just say model after it. But now, once you have this hypothesis or this model, you then use it to make a prediction. Now, what happens at that point is you make a prediction, and that prediction has to be falsifiable. It doesn't have to be able to be proved true. It has to be able to be proven false. So that's why I said it's falsifiable. If you make predictions that aren't falsifiable, you're doing pseudoscience. You're not doing anything that's really science at that point. So it's important that you understand that. You have to be able to unambiguously say, here's my hypothesis, and here's my prediction from that hypothesis. And if the number comes in between here and here, then I say my prediction was correct. If it comes outside of there, then my prediction was wrong, and therefore it's been falsified, and you have to throw it away. If, however, you get it right, then the next step is to, well, actually, before that step, once you've made the prediction, your next step is to do the observation again. This could be an observation, this could be an experiment, or this could be a test. But the main thing is you are ultimately testing your prediction. And if the prediction is right, then yay, you go and keep going. You don't stop asking questions. You don't stop hypothesizing. You don't stop predicting stuff. So you keep going around this cycle over and over and over again. If the claim that you're hypothesizing is big enough, something not so simple as just, the path of a ball thrown by a toddler is a circle. That's not enough to be a full, robust theory about how matter behaves or something like that. But if you're doing something like Newton's laws of motion, you can see that's clearly a full framework that handles a large amount of science. But the main thing is in going through this cycle of observation, hypothesis, prediction, observation, hypothesis, and prediction, if you go through that, let's say hundreds of thousands, even millions of times, and never once find your predictions to be falsified, then you're starting to move from this being a hypothesis with a model to this being a full fledged theory. Okay, theory is supposed to be a strong word in science. So when people say things like it's just a theory, that's a misnomer. That's a misunderstanding of the word theory as it's currently used. When they say it's just a something, what they really mean is just a hypothesis. Okay, because that's something that hasn't necessarily been tested enough to have some confidence in it. Whereas a theory is a very big surprise if a theory is overthrown. However, it has to be allowed to be overthrown. Okay, we can never, ever, ever, ever in science prove something beyond the shadow of a doubt as 100% right, because that would then make it dogma. Our whole purpose is to leave it open ended so that any one experiment done later in time, if done properly and in a way that someone can repeat that same experiment and it proves a theory wrong, then there's no ifs, ands, or buts about it. We have to throw away that theory in some sense. Okay. Now, we do have the correspondence principle, which says, hey, if you find a theory that better represents the data than the old theory, then that new theory better include the old theory as a subset of it. Meaning, if you apply that new theory in the realm where the old theory worked, it better give you the same answers that the old theory did. And that's exactly what helped Bohr lead people to find out and understand ultimately what quantum mechanics was. So that's my picture of sort of the scientific process and the way science works. Your book makes a point to tell you about observations, theories, laws. He gives you some very plausible definitions of them. And as I said, if you're taking the practice test or the online test or the face-to-face test, if they ask you any questions about terms like precision, accuracy, hypothesis, model, prediction, observation, theory, law, you need to answer it as the book tells you. Okay. But this is just me trying to give you a feel for how things work. Okay. Any questions on that? All right, so that really is a idea of how science works, and hopefully you get an appreciation for it. For instance, the special theory of relativity is probably the single most tested theory in the history of mankind, and the reason why is because we basically have particle accelerators all over the planet, and these particle accelerators run for months on end, and they do literally thousands of collisions or observations every second. And when you're doing that many, obviously humans can't look at it. So humans have to write computer code to look for anomalous behavior. And that anomalous behavior would include violations of special relativity. So what we're seeing is when we run these accelerators, one accelerator running for 3 months is going to get literally on the orders of tens or even hundreds or even thousands of results every second. And if none of those pop up as a violation of the special theory of relativity, then they're all confirming special relativity, and therefore special relativity is being tested on the orders of millions of times per month by a single accelerator. And we have, tens of thousands, if not hundreds of thousands, of accelerators around the planet. Quantum mechanics is a good tested theory. The general theory of relativity is still being tested to this day. In fact, in 2015, we finally proved two major aspects of general relativity to be correct. In other words, I shouldn't say prove. We found two major predictions of general theory of relativity to be correct in 2015. That was literally 100 years after Einstein wrote his general theory of relativity. Okay. All right, so that's a little bit about how science works. Your book then goes and talks about models, theories, and laws. Theories and laws are not discovered, they are invented. It gives you those little key parts. Then he talks about measurement, uncertainty, and sig figs. I'm going to deal with that well, you're going to deal with that in your lab with your lab instructor. So you'll get plenty of experience with that. But I do offer documents that teach you how a proper way of figuring out how many sig figs a number has, and then figuring out how do you take two numbers with sig figs and multiply them and then round them appropriately. What about if you add those two numbers? What about if you take the sign of one of those numbers? What about if you take the logarithm of one of those numbers? I have some documents that'll be posted up for you guys to look at that'll help you with that as well. So if you need me, even though I'm not your lab instructor, by all means ask me and I'll be glad to help you. Scientific notation is something you're supposed to know as well. Percent uncertainty and sig figs and approximations and accuracy versus precision are all things you're supposed to know. So just make sure you read this material really well and ask me questions if you don't understand it. Okay, I'll be glad to talk about it ad nauseum if you have any questions. I'm going to go on to units and standards. So, what I want to tell you is, in order for us to do science, we have to agree on certain things. So, when we're doing science, it's very important that you and I, who might be on different sides of the globe, are in a bigger perspective. I might be on planet Earth and you might be on planet Vulcan, okay? Which obviously is a mythical place from Star Trek, but still, the point is, in a future reality, there might be alien species that we interact with, and we should both discover the same laws of physics, even though they might not be said exactly the same way, and they're certainly not going to be called Newton's laws or Einstein's special theory of relativity. But if the society is advanced enough, they should have discovered the same things we should. In order for that to happen, we all have to agree on certain definitions. So we have to agree on if we're going to have a law of conservation of momentum, then we're obviously going to have an agreement about what conservation means. We're also going to have an agreement of what momentum is and what linear momentum is and what angular momentum is and all the other quantities that go into it, like impulse and force and mass and velocity. So to that end, we had to come up with a standard set of units and a standard set of uh, quantities of measure. So I'm going to go ahead and turn to another page. And for this, I'm going to give you a little intro to the System International. So the SI system is what most people used to call the metric system. And what it is a more rational system of units. Like you probably know that there's well, I can't remember the number of teaspoons in a cup, but that's one of the weird measurements you'd want to know with this old system of units. You'd want to know how many teaspoons there are in a tablespoon. That's three. All right, how many tablespoons are there in a cup? If I remember correctly, a tablespoon is 15 milliliters, and a cup is supposed to be 250 milliliters. So if you divide 250 by 15, that should be roughly it. But the main thing is we also know that a cup is 8 ounces, and we know that there's 2 cups in a pint, and then that there's, I think, 2 pints in a quart, and then there's 4 quarts in a gallon. that's a bunch of historical units that meant something at the time and had historical significance for the numbers that were relating them, like, 2 quarts being in a pint or something like that, or excuse me, 2 pints being in a quart or something like that. That's something that is just a historical artifact. It's not a rational way of splitting up your units. So after the Enlightenment, which is part of the reason America was founded to begin with, we started doing things like that. We tried to come up with more rational systems of units, and at that time, France was one of the major world powers, and therefore we came up with the metric system or the System International. And then later Napoleon gets in office, and all sorts of heck breaks loose. But the main thing is, we were able to generate a system of units. Originally, it was what we call the CGS system, which means centimeters, grams, seconds. So that tells you that evidently there's some fundamental quantities. CGS, centimeters, is a unit of length. G is a gram, that's a unit of mass. And seconds is a unit of time. So evidently, length, mass, and time are sort of fundamental quantities. So we need to all agree exactly what length is, what mass is, and what time is. And then we also need to understand and agree what the fundamental unit would be. So when we were calling it the CGS system, the fundamental unit of length was the centimeter, and the fundamental unit of mass was the gram, and the fundamental unit of time was the second. So we needed to define exactly what a centimeter was, exactly what a gram was, and exactly what a second is. Well, the modern SI system is more of what we call the MKS system, which is meters, kilograms, seconds. But notice that last time we had an actual prefix on the unit of length, the centimeter instead of the meter, and we had no prefix on the unit of mass. We had the gram instead of the kilogram. Now we have no prefix on the unit of length. We have the meter, but we do have a prefix on the unit of mass, the kilogram. So the base unit is still the gram, just like the base unit of length is still the meter, but in the SI, whenever we're using physics equations, they are expecting you to put masses in kilograms. Okay. That's the only sense that that's the fundamental unit. Okay. In every other sense, it's really the gram. But whenever you have an equation that has mass in it, they're expecting you to put in kilograms, unless you're lucky enough that the kilograms is going to cancel out with some other kilograms. Okay. So now that we have that, I can give you our system of prefixes so that you'll have a better understanding of what the system international is. And the letters I write down and the dots are important. So you might want to come up with your own mnemonic. I've stopped giving them because my mnemonics are always from the mentality of somebody in third grade or maybe fifth grade. So they're always something that's funny or about poop or pee or body parts or something. So, anyways, I won't give you my mnemonic, but by all means, make up one. So, T is for tera, dot, dot. G is for giga, dot, dot, dot. M is for mega, dot, dot. K is for kilo. H is for hecto. DA is for deca. And then we have the base unit. And remember, that's the unit with no prefix on it. Even though we use kilograms and everything in SI, the base unit is still the gram. And then the next one is the deci, and then the centi, and then the milli, dot, dot, and then the nano, or excuse me, micro, dot, dot, and then the nano, dot, dot, and then the pico. Okay, so that is the system of prefixes, and this is why it's rational. If you want to go and consider what the bases are, well, the base units can be a gram, which is for mass, it can be a meter, which is for length, and it can be a second, which is for time. As the semester goes, we'll learn other quantities as well. For instance, we'll learn the unit of charge or the unit of energy or stuff like that. A lot of those things can still be made out of the M and the K and the S, but some of them are brand new. Like the coulomb for charge is either brand new or the ampere is brand new. You can define the ampere as a coulomb per second, or you can define the coulomb as the amp second, depending on which one you want to call the fundamental unit. So there's going to be other base units that we put in here, but right now all we know is the base units for mass, which is the gram, the base unit for length, which is the meter, and the base unit for seconds, or excuse me, for time, which is the second. If you want to find another unit that's 10 times bigger than the gram, then it turns out that deca is the unit that you want to use, the prefix. So a decagram means 10 grams. Hecto is the next one, and that is 100, which is actually 10 to the 2. And then all of a sudden you realize, oh, 10 is 10 to the 1. Okay. And then kilo is 10 to the third, or 1,000. So this is what I mean by it being rational. It's a rational system of units. Each unit only differs from the other by a factor of 10 or 100 or 1,000. Whereas the other ones were weird things like, 2, 4, 8, or whatever. Sometimes they're even, odd numbers like 2.54. Okay. Now, the dots mean something. We skipped prefixes. There's no prefix between the K and the mega. The very next one, of course, is the mega, and that's a million, which is 10 to the sixth. And the very next one is a billion, which is 10 to the ninth. By the way, Great Britain uses a slightly different version. So what we call billion, they call trillion, if I remember correctly, or something weird like that. So just keep that in mind. Sometimes other countries use slightly different versions. And then finally, tera is 10 to the 12th. So that's 1,000 billion, or a trillion is what we call it here in America. Similarly, if you go the other way, 1/10 of a gram is a decigram, DECI, decigram, and that is 10 to the negative 1. The C is centi, which you recognize as centimeter, or the cents in a dollar, both of which are 100. So you realize that a centi is 1/100th, so that's 10 to the negative 2. And a milli is 1/1000th, so that's 10 to the negative 3. Then we go by leaps of 1,000. So the next one is micro, which is 1/1 millionth, so that's 10 to the negative 6. And the nano is the next. That's 10 to the negative ninth, or 1 billionth. And then pico is the next one, and that's 10 to the negative 12th. And that would be 1 trillionth. Okay. So by writing it this way, this was a way we used to teach, for instance, biology majors, because back in the day, biology wasn't very mathematical. Biology is a lot more mathematical now. So a lot of biologists have some pretty good math credentials. But back in the day, you would just give them this, and then all they would do to convert units is the following. Let's say, for instance, I wanted to convert, let's say, 3, 4, 5, 6, 7, 8, 901, 2, 3, 4 nanometers, and I would like to convert that to, let's say, megameters. Okay. So the way you can use this little assemblage, and by the way, this isn't the way you should be doing it in physics. I'm just giving you a life rope in the event that you get really stressed out and can't figure out how to solve one or convert one unit. I'm giving you a quick and dirty way of doing it. So what you do immediately is you mark off what the unit you have is. So we're looking at nanometers. That means we're right here at the nanometer. And then you make another mark, like a target, if you will, for where you're wanting to go. Well, we're wanting to go right here, so I'm going to say that's my target. And then you count the number of moves. You don't count the number of places, you count the number of moves that you have to make to go from where you are to where you want to be. And each dot or each letter is a place, as well as that blank line. So when I go to do this, I go 1, 2, 3. That's 3 moves. 4, 5, 6. That's 6 moves. 7, 8, 9. That's 9. 10, 11, 12. We're up to 12. 13, 14, 15. So it's 15. So not only did we learn that we have to move the decimal 15 places, we learned that we have to move the decimal 15 places to the left. Okay, so the decimal in this number 34567890123 is understood by convention to be right there where I put that purple one in. So what I need to do is move it to the left 15 places. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 right there. And I still need to go farther. So I'm going to write 0.123 and then 3, 4, 5, 6, 7, 8, 901,234 mega meters. So that's how you could actually convert it just using this little system that I just made up, okay, or that I just showed you guys. Uh, if I wanted to go the other way, obviously I would be given like a really small giga number or tera number or something like that, and I might want to convert it to something on the other side, say pico or something like that. Then do the same thing. I'd put a arrow at the units that I have and then put a little target at the unit I want. And then again, I count the jumps that I have to make to get to that other side. And I make note of which direction I go. And sure enough, that's the number of places I have to move my decimal and the direction that I have to move it. And that will always, always, always work. Okay. It's just not very helpful because it's not time saving. It takes too much time to do that. If you do it in your head, then that's great, but it's really easy to make that mistake when you're on a test and trying to guess your movements of your decimals. But that is a way to do it. A more robust way is what we call the factor label method. And the factor label method hinges on the idea that when you have a number, if you add to it anything other than zero, it's going to change. Okay. If I have a number and I add a number that's not zero to it, that number is going to change. So uh, I could add a number to it only if it's zero if I just wanted to convert units. But it turns out there's not any kind of units that work that way. Another thing to know is that if I want to multiply a number by another number, if I multiply that number by something other than one, I'm going to change its value. And I don't want to change its value. I'm wanting to convert its units to another form. So, in other words, if I want to convert units, one way we can do that is by multiplying by one. And then we just have to recognize that one has a lot of different forms. For instance, one is the digit one. It's also 1 over 1, but by that standard, we also know it's 2 over 2. Or, a little more abstractly, we could say it's pi over pi. That would be fine. And if we want to get even more abstract, we can think in terms of a little bit broader terms where it's not even two just plain numbers, but numbers that have units, denominate numbers. We could say, for instance, 1 foot is equal to 12 inches. But by that right, we could also say 12 inches is equal to 1 foot. All of those are values of one. It's just a matter of figuring out which value of one is most helpful. So, as my first example, I'm going to do a really long, drawn out calculation of converting the units of 60 miles per hour to meters per second because meters per second is what we use. So we're going to do that real quick. Let's do 60 miles per hour. And first thing I want you to learn is when you're converting units, it's best that you go ahead and write your initial number as a fraction. So in this case, you could just write miles per hour and then put it over one because you're always allowed to put a number over one, and that makes it a fraction. The reason why I'm telling you to do this is because it's really important that you understand which numbers are in the numerator and which numbers are in the denominator. So what I would do with 60 miles per hour, I would recognize that the per means divide, and I would say that 60 miles divided by 1 hour. You didn't have to put that one down there. I could have just left it as an hour, but it doesn't make much sense without a number down there. So I went ahead and put the number with it as well. And I also want to point out that the number 60 is actually being multiplied by the mile, and the number one is being multiplied by the hour. That's something that you need to sort of get right in your head so that you'll understand how this factor label method works. Now, what I'm going to do is convert it to meters per second, and I'm going to do it using quantities that I know are exactly correct. Uh, by doing that, that means that whatever number I put in, if I have 54 sig figs in the number that I put in, then by doing it this way, I will get 54 sig figs out. If I had a million significant figures going in, I'd have a million significant figures coming out because I'm using exact quantities. You can look up a conversion factor between miles per hour and meters per second, but it's almost certainly going to be an approximation. Whereas this is no approximation. So you don't have to always look for that. Approximation is really good enough, but this is a good opportunity for me to show you how you can do many steps at once. So the first thing I'm going to do is address the numerator, and the numerator is in miles, and I want to convert that to meters. So the first thing I can do, dang it, I changed it to the wrong color. The first thing I can do is realize that 1 mile is equal to 5,280 feet. Now notice I put a single hash mark for feet. That's because I also wanted to teach you that the unit of feet can be basically listed as an apostrophe. Okay, a double apostrophe is the unit of an inch. So that's another thing I want to teach you, and you'll see that in a second. So now what we see is by me putting the mile on the bottom and multiplying by this fraction, that means the mile on the bottom can cancel out with the mile on the top. So that's part of the reason I was telling you that the number is being multiplied by the unit so that this operation makes sense. Now you can see why you can do that because it's like 60x over 1x. Okay. Now I'm up to feet per hour, but I need to go ahead and get rid of the feet as well. And what I know is 1 foot is equal to 12 inches. So that's the double hash mark that I was telling you also works as a unit for inches. So in this case, I'm going to say that the inch canceled out with the inch. Notice how I used a different slash mark for both of them. This is good bookkeeping. It allows you to look back and see exactly what you canceled what out with. And that way, if you made a mistake, you can catch it a little more quickly. So I highly recommend it. So now we're up to inches per hour. Now, a good thing that I happen to know is an exact conversion between the MKS/SI system and the British system, which is the system of units we use. It's called the British system, but the Brits don't use it. It's literally like us in Myanmar. That's about it. I think Liberia maybe too, but we're the only countries that use it. So now I'm going to use another value of 1. This time I know 2.54 centimeters is equal to 1 inch. So do I want the inch on the bottom or do I want the inch on the top? Anybody can tell me that? 2.54 centimeters is equal to 1 inch. Do I want to put the inch on the bottom or the inch on the top? Well, we're trying to get rid of it, so I'm going to put 1 inch on the bottom, and I'm going to put 2.54 centimeters on the top. And now my cross out mark will be a full red X. So now I'm up to centimeters per hour. You can see everything's canceled out except for the centimeter on top and the hour on the bottom. Now I can look up at my table here and realize that the centimeter is 1/100th of a meter. That means there's 100 centimeters in 1 meter. So I can now make another value of 1 by using 100 centimeters is equal to 1 meter. It's just a matter of figuring out, do I want the centimeter on the bottom or do I want the centimeter on the top? Anybody have an answer for that one?
Bottom.
Very good. So I'm going to say 100 centimeters on the bottom. and 1 meter on top. And now it seems like I've completely exhausted my ways of slashing things out. What I often do will do a wavy slash mark. So that's my wavy slash mark to cancel out the centimeters. Now I'm up to meters per hour, so that's a pretty good start. I just need to convert the hours to seconds, and I'm going to do it in 2 steps, though I know you probably can figure out how to do it in 1 step. So the next thing I need to do is I realize that 1 hour is equal to 60 minutes. Now let's see if you can answer this one. Do I put the minutes on the top or do I put the minutes on the bottom? Or let's actually make it a fair question. Do I put the hours on the top or the hour on the bottom with this value of 1? We're trying to get rid of hours. Do I put the hours on the top or the hours on the bottom? Go for it, Zane, if you know it.
Top.
Yep. So we're going to say 1 hour on top is equal to 60 minutes on the bottom. And now I'm going to do my slash the other way. It's a curvy slash this way. So that's going to be a curvy slash that way. Now I've got it to meters per minute. And I got one more step. This time I've got to realize that 1 minute is equal to 60 seconds. So I'm going to put the minute on top and say 1 minute over 60 seconds. And now I can see that this minute is going to be a curvy X and it cancels out. And finally, I'm going to write equals. Now, how do you deal with this monstrous looking construction? Well, what I tell my students to do, and you should do this until you get the training wheels off, you should multiply all the numerators 1 times 1 times 1 times 1 and get a new numerator, and then multiply all the denominators to get a new denominator. And that's the first step. So let's first off multiply all the numerators. So I'm taking 60 times 5280 times 12 times 2.54 times 1 times 1 times 1. That gives me a really big number, 9,656,000. 9,656,000 64. And notice the only unit on top left is the meter, so I'll put that up there. Notice also how I'm writing my numbers in pods of 3. Please always do that. It doesn't matter what end you start from. Don't worry. Don't obsess about that. Just start it in pods of 3. That way I can easily see, because when you have strings of zeros or strings of 1, it's really hard to see. All right, now I'm going to do all the denominators. So I'm going to say 1 times 1 times 1 times 1 times 100 times 60 times 60, and that'll give me my new denominator, which is 360,000. And the only unit left in the denominator is seconds. So now you see I have two numbers, one for the numerator and one for the denominator, and all I have to do is divide them. So I'm going to take the 9656064 and divide that by 360,000 and hit enter, and that gives me 26.8224 meters per second. Now, that's way more sig figs than I put in. I only put 2 sig figs in, but that is the actual answer. So even if I had carried 50 decimal places on the 60 miles per hour, it was 60.000000, 50 decimal places. This would still be the right answer. Okay, because I use these quantities that are 100% right, not approximations. You don't need to worry about doing that. You don't have to do that ever. I've just you to understand that that's the advantage of using this particular long method. You could get rid of the 60 at the front, just divide that quantity by that. So let's say divided by 60. And then what you see is 1 mile per hour is equal to 0.44704 meters per second. That's the actual conversion factor, and that's it to an infinite number of decimal places. So that's another way you could do it. And if you looked it up in the book, you'd probably find 1 mile per hour is equal to 0.447 meters per second. And that's close enough. That gets you three sig figs. Anybody have any questions on that? Good job. I did see, Gray, that you had written bottom in your chat. I just didn't notice it until after I'd already gotten an answer. So sorry about that. All right. Now, another thing I need to discuss with converting units is this weird thing where sometimes you have a unit raised to a power. So I want to show you how to do that. And I'm going to use the density of water as an example. So for instance, I know that the density of water is equal to 1,000 kilograms per cubic meter. Now, a cubic meter is like 39 and an eighth inches by 39 and an eighth inches by 39 and an eighth inches. And that's pretty big. A meter is about the height of a doorknob. So to the top of your doorknob on your bedroom or top of your doorknob in your classroom or whatever, that's about what a meter is. And you should start getting used to that. A centimeter is about the width of your middle finger nail. So the width from this edge of your fingernail to that edge of your fingernail, that's probably about a centimeter. The thickness of a staple, the actual thickness of the metal itself, that's about a millimeter. Those are the kind of things you want to think about, especially when we get into the rapid estimation stuff that we'll do next time. But anyways, now that you know that, you can imagine that's a big quantity of water. You've probably seen trucks riding around with a big white plastic tank inside of a metal silver cage. That's a cubic meter of water. And it says by this density that 1 cubic meter of water weighs 1,000 kilograms. If you've been in the medical field, you know that a kilogram is about 2.2 pounds. So this is 2,200 pounds is what a cubic meter of water is. A ton is 2,000 pounds. So this is what we call a metric ton. The regular ton that I just told you, 2,000 pound, that's called a short ton. But that just gives you an idea of roughly how dense water is and how heavy it is. So what we would like to know is what is this in grams per cubic centimeter? So that's the unit conversion we're going to try to do now. And you'll see, by the way, I have an extra credit assignment for converting density of water to various other quantities. And you'll see water is really unique. It has a value very close to one in several different types of units. So by all means, do that extra credit and turn it in there. But let's go ahead and do the unit conversion. So I'm going to write this as 1,000 kilograms divided by 1 cubic meter. Now the kilogram's pretty easy because I can look up here and see that a kilogram is 1,000 grams. Remember, this one said a centimeter is 1/100th of a meter. But in this case, I'm going to the left, and this is a positive exponent. So it's 1,000 uh, meters is equal to 1 kilogram, or 1,000 grams is equal to 1 kilogram. So let's go ahead and handle that first because it's really, really easy. I'm going to say 1 kilogram is equal to 1,000 grams. So that way already we've managed to convert it to grams per cubic centimeter. Okay. But the main reason I'm doing this example is so that I can teach you how to deal with the meters cubed. So let me show you what that is. You might already know, and that's good, but I just want to make sure everybody knows how. So what we know is looking at the centimeter versus the meter, we know 1 centimeter is 1/100th of a meter. Or alternatively, you can say that 1 meter is 100 centimeters. So I'm going to say 1 meter on top because our cubic meter's on the bottom. 1 meter is equal to 100 centimeters. Now, that meter cubed means meter times meter times meter. So I've got to do that 3 times. So now I say another 1 meter over 100 centimeters, and I say another meter over 100 centimeters. And now what you can see is this meter, and this meter cancel out with all three of those meters. And we're now going to get grams per cubic centimeter. Now, the math on this is really easy because what we see is we had 1,000, and then we multiply that 1,000 by 1,000, that gives us 1,000,000, and then we multiply it by 1, by 1, by 1, so I still have 1,000,000. Notice how I'm writing the numbers in pods of three. You can even put commas in there. There's a very specific way you're supposed to put the commas in, that's why I told you you don't have to worry about putting the pods of three in any specific order. But if you did parentheses, you really need those to be in the right places. Okay, so what we have is 1,000,000 grams for the numerator. And what we have for the denominator is 1 times 100, that's 100, times 100 again, that's 10,000, times 100 again, that's 1,000,000. So I got 1,000,000 grams divided by 1,000,000 cubic centimeters. And that means the density of water is 1.000 grams per cubic centimeter. Okay, so now you've learned how to deal with the actual fact that these cubic or that the meter was cubed. If the meter's cubed, you're gonna have to do the conversion twice. If the meter or three times. If the meter's squared, you're gonna have to do it two times. That sort of thing. So just keep that in mind. I will tell you that also 1 liter. If you write a triple equal sign like that, that means is defined to be. So the liter is defined to be a cube that is 10 centimeters on each side. So 10 centimeters by 10 centimeters by 10 centimeters. That is 1 liter. We know that the volume of that block that I just drew is equal to 10 centimeters times 10 centimeters times 10 centimeters, which equals 1,000 cubic centimeters. But we know that's also defined to be 1 liter. So what that means is, therefore, 1 milliliter is equal to 1/1000th of a liter, which equals 1/1000th of 1,000 cubic centimeters. Notice I just used this fact right here. 1,000 cubic centimeters is equal to 1 liter. There's the 1 liter. There's the 1,000 cubic centimeters. And I used the fact that a milli is 1/1000th. So now what we see is that 1 milliliter is exactly equal to 1 cubic centimeter. That's something that'll smack you in the face as soon as you become old enough to become a parent. For instance, when you go to your pediatrician for your baby that's sick and they write you a prescription that says, give your child 5 cc's of this medicine every 6 hours, and then you take it to the pharmacist and they write the prescription or they give you the prescription, and on it it says, give 1 cc or 1 milliliter every 6 hours. And you're like, wait a second, this is just different from what the prescription said. Well, no, it's not. It turns out that a milliliter is exactly the same as a cubic centimeter. Okay. Anybody have any questions of that? All right, so that is how we do unit conversions, and I want to tell you that in addition to unit conversions and a system of units like we have in the SI, which is basically what we're going to be using this whole semester, there are other system of units, and there's other ways to convert units. For instance, if you're familiar with converting between Fahrenheit and Celsius, there's a linear equation that relates the two. It's like y equals mx plus b, only you could replace the y and the x with F and C for Fahrenheit and centimeter, or for Fahrenheit and Celsius, or Fahrenheit and centigrade. That was another phrase that they used to use instead of Celsius. But that's fine as well. That's just an entirely different type of unit. And actually converting between Kelvin and Celsius is also a linear expression, but it's a really simple one that has a slope of 1. For instance, the equation y equals mx plus b for Celsius to Fahrenheit, the temperature in, or excuse me, for Celsius to Kelvin, the Kelvin temperature is the Celsius temperature plus 273.15. Similarly, if you were looking at the Rankine system and the Fahrenheit system, the Rankine is like a Kelvin, but for the Fahrenheit system, and it's shifted down just like the Kelvin is. And I can't remember the number, but I want to say it's around 456 or 564 or something. So whatever that number is, the temperature in dang it, I never got the units. The temperature in Rankine, excuse me, the temperature in Rankine is equal to the temperature in Fahrenheit plus that number, which, like I said, is 546 or whatever. Now, the temperature in Fahrenheit versus Celsius, what you could do is you'd say uh, Fahrenheit equals m times Celsius plus b, using the form y equals mx plus b. You can take the fact that freezing of water happens at 32 degrees Fahrenheit and 0 degrees Celsius, and boiling happens at 100 degrees Fahrenheit and 212 degrees Celsius. You can use that first data, the 32 and the 0, to solve for B, and what you'll find is B is equal to 32. And now you can use the other data. Now that you know B, you can use the 100 and the 212 to find out M. And what you'll find out is M turns out to be 9/5. Okay, so that's a way you can always derive the expression for converting units between Fahrenheit and Celsius. So that's another type of unit. It's converted an entirely different way, so this factor label method doesn't work. There's another one too called the decibel, and what you might not recognize is the word deci in decibel is an actual SI prefix. So the actual definition of the decibel is 10 times the log of the quantity divided by some standard value. So that's another one that doesn't work by the factor label method. Decibels are not just used for sound, by the way. They're used for the intensity of an electrical signal. It can be diminished by a certain number of decibels, so it actually applies in sound as well as other things. All right, now that we've finished that, I've talked about all the different types of units. I want to let you know that there's also a good deal of work that has to be done with regards to these standard units. The gram, the meter, the second are in this case the kilogram, the meter, and the second. So initially, what we had for the meter was a platinum iridium rod that had two etch marks in it, and the distance between those little etch marks was defined to be 1 meter. And we kept it in a tight environment where air wasn't able to circulate around it, so it didn't pick up dust and get oxidized, do rust and stuff like that. And we kept the temperatures really fixed, so it always stay at exactly the right length. Because if you actually heat it up, it's going to get longer. If you cool it down, it's going to get shorter. And we do all that. And then every year or so, you could pull that one very important rod out, and other countries could come along and bring their sort of their model of that rod and check it against that rod and correct it, and then take it back home and use that for a while, and then next time around they can come back and do it again. That was the way things standard units were built, and they were actual physical objects, which is not that convenient. Ideally, what you'd like to be able to do, especially if we ever meet any alien races, is we'd like to be able to communicate a method by which we can determine exactly how long a meter is, and we wouldn't have to ship a physical object anywhere. Okay, because there's a lot of things that could be damaged in just in the shipping process that could make it not accurate, and as well as other things. So it's better to have some kind of process or some kind of physical manifestation that shows us what it is. So some time ago, we were able to switch away from that meter long bar, and what we decided to do was we first had to define the unit of a second. Now, originally, the unit of a second, if I remember correctly, was supposed to be 1/86,400th of a day. So you'd actually have to figure out how long it takes for the sun to be at one spot in the sky and then be in exactly that same, over that exact same longitude later. That would be the exact 24 hours. And then you would divide that up into 24, and then you divide that up into 86,400 parts of an hour. And that 86,400, I think that's what it should be, 24 times 3,600. I think that's 86,400. I just happen to remember it off the top of my head. So hopefully it's right. If it's not, you know the point. And that was how we defined a second. But as we studied it more, we realized that the length of a day is actually changing. We have leap seconds that the International Bureau of Standards and the American Bureau of Standards has to change on occasion. Okay, because the sun is, or excuse me, the moon is actually pulling on us in such a way that it's slowing our rotation, and the distance away from the moon is from us is actually getting farther as well, and all that's combining to make us lose what we call leap seconds every now and again. So we have to correct it. So the idea of a second being 1/86,400th of a day of a, maybe it was a day, uh, that actually became a problematic definition because the length of a day wasn't even set. So what we did was we discovered that there's this element, cesium 137, that has radioactive isotopes, and that radioactive isotope of cesium 137 actually decays in such a way that billions of particles disappear every second, literally billions of them. So what we decided to use was that to define our unit of time. And there's a very specific number. I can't remember it. I think your book gives you exactly what the number is. But basically, if you take and set a Geiger counter next to a sample of cesium 137, which obviously any culture can do as long as they have the element cesium, they can get cesium 137. And then as long as they have cesium 137, they can build a Geiger counter and put it right next to it. And when you build that Geiger counter and put it right next to it, what you'll do is you watch it, and slowly but surely, the Geiger counter is going to count disintegrations of nuclei. And it'll go one, two, three, four, five, six, seven. Every time a nuclear decay occurs, it increases the count by one. If you keep doing that over and over and over again, uh, specifically, it's not that one. I think I found the number that I was looking for with regards to cesium 137. Nope, that's not it. That's not it either. I was hoping I'd found it. Crap, I seem to have not found it. Oh, here it is. Yeah, there it is. So if you wait for that Geiger counter to reach 9,192,631,770, once it reaches that 770, boom, that's 1 second. Then you wait again for 9,192,631,770. Once it gets there, that's another second. So that's our modern definition of a second. It's the time required for cesium 137 to decay 9,192,631,770 times. That's the new standard of what a second is. Now that we have that second, it turns out that that second is like so precise that it's only off by maybe 1 decimal place in the ninth decimal place. So 10 billionths of, or 1/1 billionth of a second is what it's off. So that's a very, very precise measure. We know exactly how far off it is, so we can even correct it as needed, but it's perfect for us. So we use that. Now that we have this really precise definition of a second, we can use that to define the unit of a meter. So what we did is we took the speed of light, c, is approximately 3.00 times 10 to the eighth meters per second. And we've known that since the time of Maxwell, since the 1800s, basically. We've been pretty close to it even in the 1700s, but the 1800s, we got really, really close. But now what we've done is we went ahead and defined the speed of light to be a fixed number. So the speed of light is now defined to be 299,792,458.0 with a bar over it meters per second. That means it's defined to be exactly that to an infinite number of decimal places. Okay. So with that in mind, we can now say that 1 meter is the distance light travels, and specifically in a vacuum, in 1 over 299,792,458th parts of a second. So now that we have the second so well defined, we can just divide the second up into 1 299,792,458ths of a second. And the distance that that light travels in that time period is now 1 meter. So that's a more usable and prescriptive definition of the meter, and we could communicate that to anyone, any alien species, for instance. We don't have to physically take something there. Now, we're in the process of doing the same thing for the unit of mass, but we can't. Okay, we haven't yet figured out a way to do it. So we actually have a physical object for mass. So the kilogram is a platinum iridium cylinder. And again, we're using platinum iridium specifically because it's not easy to oxidize, so it doesn't accumulate a lot of extra weight easily on its own. Uh, and we'll say specifically it has a radius R and a height H. Okay. And we define this platinum iridium cylinder to have a mass exactly equal to 1 kilogram. Okay. Since it's platinum iridium, that means it's a fixed quantity and therefore has a fixed density. And density, hopefully y'all remember, looks like a heart. This is what I hear they teach in high school. Density looks like a heart. So now you see density is mass over volume. So the fact that it has to have a fixed mass, which is 1 kilogram, and the fact that it's made of a fixed material, which means its density is fixed, all of that tells us that volume is equal to a constant, as is mass equals a constant, and the density equals a constant. So the density is a constant, and the mass is a constant, and therefore the volume has to be a constant. Okay. Now, with that in mind, if we want to make something that's useful, we would really like to minimize its surface area, because if its surface area is minimized, then the amount of oxidation is minimized. So one of the extra credit assignments you can do is calculate the dimensions of this platinum iridium cylinder such that the surface area is minimized. So the volume of a cylinder, this cylinder specifically, is pi r squared h, and the surface area of the cylinder is the top area, which is pi r squared, plus the bottom area, which is pi r squared. So we've got 2 pi r squared, plus we have the area of the sort of what would be the soup label, the label of the soup can. And that has if you imagine it rolled out like a rectangle, it would have a width that's the circumference of the cylinder, and it would have a height that's h. So we know that that is 2 times pi times r, because that's the formula for the circumference. And then we multiply that circumference times h, and that's our surface area problem. Okay, so the surface area function is 2 pi r squared plus 2 pi r h, but that's a multivariable function. And until you've had maybe calc 2, but normally until you've had calc 3, you don't know how to deal with multivariable functions. So your extra credit problem, which you'll see listed in week one's module, is to minimize the surface area. And there's a very specific operation that you do in calculus y'all learned about. Can anybody recall what that operation is to find extrema like maxima, minima, or points of inflection? Anybody recall?
Is it the derivative tests?
Exactly. You take the derivative of the surface area and you set it equal to zero. In this case, it's a little problematic, and I explained it in the extra credit assignment, but it's a little problematic because it's a two variable function. So what you do is you take the volume formula, which I just wrote there, and you solve it for either H or R. And then you plug that in for H or R in the surface area, and then the surface area is now only a function of H or R, depending on which one you got rid of, and volume, which is a constant. So then you take the derivative of that with respect to that one variable, set it equal to zero, and then solve for that one variable R or H. Once you get what that R or H is equal to, you then plug that back in the for the volume, because it's going to have a volume in it. You plug that volume formula back in, or that H formula or that R formula back in, and what you'll have is a relationship between R and H that tells you how to minimize the surface area. Only you can't be sure it's minimized because there's a second test you got to do. Hopefully I'll remember what that is, but I'm getting ready to tell you. So the other part of the extra credit is once you find that relationship between the radius and the height of that cylinder, then you got to confirm that that is in fact a minima, not a maxima, and not a point of inflection. So what you then do is take the second derivative of that surface area. Remember, the surface area still has to be one variable. So you're going to, that derivative that you calculated, the derivative of the surface area in one variable, you're now going to have to take that derivative, the derivative of that to get the second derivative. And then you're going to plug in the relationship between R and H and see if that second derivative is positive, zero, or negative. If it's positive, then you know that it is a minima. If it's negative, then you know it's a maxima. And if it's zero, you know it's a point of inflection. And in case you ever forget that, just remember this one function that everybody that's been through pre-calculus should know. This one function, y equals x squared, is a perfect example of a minima. Specifically, the minima is right there, and dy over dx is equal to 2x. And when you set that equal to 0, that gives you x is equal to 0. Then when you take the second derivative of y with respect to x squared, that's the derivative with respect to x of 2x, and that is just 2. So you see that when it is a minima, it comes out to be a positive. So that's what I use just to remember it myself, as I always refer back to the y equals x squared in case you forget. Anybody have any questions on that? Okay, you'll see both of those extra credits that I just offered you listed in the extra credit section in week one module. And there, I usually give you about 2 weeks to get them done. So I highly recommend you do them. They're just extra credit, and they're going to take the place of one whole homework assignment. So, by all means, do it. There's also one later that you'll learn where I tell you to divide 1 by 243. That's pretty fun. You'll see it later, though. All right, before we move on, anybody have any questions? Okay, so I've covered the units. I've covered the standards for the base units so that we know, for instance, that the meter used to be a rod, but now it's the distance light travels in one 2 over 299,792,458 of a second. And we know that the second is the time required for about 9 billion nuclear disintegrations of cesium and our transitions of cesium. And with that, you can now have some understanding of how the base units are put together. But now I want to talk to you specifically about dimensional analysis and unit analysis. They're really the same thing, but when you use a quantity like the dimension of mass is capital M, or the dimension of length is capital L, or the dimension of time is capital T, then you're doing dimensional analysis. If you're working with the unit of mass being the kilogram and the unit of length being the meter and the unit of time being the second, then you're doing what we call unit analysis. So I should start off by letting you know that when I say units are dimensions of a quantity m, for instance, which would be mass, the dimensions for mass are capital M, and the unit for mass is equal to the kilogram. Similarly, the unit for length, the dimension is L, the unit for length is the meter. And notice how I'm using capitals for dimensions. That's to help me not confuse it with M for meter and stuff like that. And the dimension for time is capital T, and the unit for time is the second. Okay? So let me show you one way that we can use dimensional analysis. For instance, you probably know of one or two equations from physics already. I wouldn't be surprised if you did, anyways. Uh, and one of the equations of physics that you might know, I'm not even going to tell you, just let you see it pan out in real time. But there's a quantity that is energy, and the energy is a function of mass and velocity. So let's say energy is E, and we're going to say that we expect this quantity E, the energy, to be dependent on mass and velocity. Okay, so energy is a function of mass and velocity. Now, we can use just that principle. Hey, I'm assuming that energy depends only on mass and velocity. I would like to postulate an equation for energy that may or may not be right, but at least is dimensionally or unit wise, it's correct. So, what is a plausible equation for energy based on mass and velocity? Okay. In order to do this, I have to tell you that the dimensions for energy is equal to m L squared over T squared. That's the dimensions. If I wanted to do it in units, I would use kilograms, meters squared per second squared, but I'm going to do dimensional analysis here. I also have to tell you that the unit for mass, or the dimension for mass, is capital M, and the dimension for velocity is length per time, so that's L over T. Okay? So let me show you how to use dimensional analysis to derive a formula for E. use dimensional analysis to derive a formula for energy as a function of m mass and v velocity. So here's how I do it. I'm going to say E dimensionally is equal to m L squared over T squared, which I can also write as m to the 1, L to the 2, and T to the negative 2. Did everybody follow that? Anybody not understand what I just did there? I do have the chat window open in case anybody types it instead of saying it. So let me know if you have any questions. Also, if anybody hasn't chatted me your first and last name, go ahead and do that now if you haven't already. Now, I also want it to be a function of mass and velocity. So I'm going to set that equal to the mass. Well, let's do it this way. I'm going to say E of m and v is equal to mass raised to the p power times velocity raised to the q power. I can't add mass and velocity because they have different units and different dimensions, so you can't add unlike quantities. I can't subtract them for the same reason. I can multiply them and I can divide them, but in writing it this way, the q could be a negative quantity, in which case I'm dividing mass by velocity, or the q could be positive and the p could be negative, in which case I'm dividing velocity by mass. So this covers all the ways you could multiply them or divide them. And if it had multiple terms, they would still, if they both included m and v, then they'd still have to be of the same form as this. So this is the most general expression that I can write for an equation that is related to only mass and velocity and gives the energy. In order for me to make it plausible, I have to make sure the dimensions on the left equal the dimensions on the right. So the dimensions on the right are going to be mass raised to the p power, and that means m to the p, and they're going to be velocity raised to the q power, and that means it's going to be L over T raised to the q power. So I can simplify this velocity one a little better and call that L to the q times T to the negative q. Now I can combine this. I'm going to take the left-hand side, the m to the p times the v to the q, and I'm going to set it equal to the dimensions on the left-hand side, which is the m to the 1, the l to the 2, and the t to the negative 2. So E dimensions is equal to m to the p, v to the q dimensions gives me the following. M to the 1, L to the 2, T to the negative 2 is equal to M to the P and then L to the Q, T to the negative Q. Everybody follow what I did there? Okay, now my job is to just figure out what P is. Well, M only appears once on the left-hand side and only appears once on the right-hand side. And in the left-hand side, the M has an exponent of P. So I can say from looking at the M variable, we have that 1 is equal to P. So I'm going to call that equation 1, and that's probably, this is such a simple example. I won't even need to label the equations. I'm just doing that to get in the habit of it for you guys. Now, the next one is the L variable. The L variable, On the left is raised to the 2 power, but on the right it's raised to the q power. So that suggests that q must be 2. But I haven't satisfied all the equations yet, so I still got to make sure the third one, which is the t equation, I still got to make sure that's valid. So the t term or the t factor is going to give us on the left hand side, it has an exponent of -2, and on the right hand side, it has an exponent of -q. So that suggests that it's consistent with equation 2 in that -q equals -2 is the same thing as q equals 2. So really, there was no need to label these equations because I don't have to combine them to solve it. I've just figured out that evidently, if I want to make this function, then I have to make sure P is 1 and I have to make sure Q is 2. So that's it. We can now say that energy E as a function of mass and velocity has got to equal m to the p. That means m to the 1 power, and we normally don't write a superscript of 1, and then v squared. So if you think in terms of Einstein's famous equation, we got it. In that case, though, we were actually specifically talking about the speed of light instead of just random speed. So we would actually derive E equals mc squared just by using dimensional analysis. That's what we just succeeded in doing with no understanding whatsoever of the physics behind this. All we know is that mathematically speaking, when you have an equation, not only do the numerical parts of the two sides of the equation have to be equal, but the dimension part or the unit part of each side has to be equal as well. And just using that fact, we were able to derive a formula of mv squared or a formula of mc squared. What we do know, by the way, is that kinetic energy is equal to 1/2 mv squared. So we were just off by a factor of a pure number, 1/2. But there's also Einstein's famous E equals mc squared. And in that case, we got it right on the money. So that's how awesome dimensional analysis is. Anybody have any questions on that? All right. Well, your book does this really nice example, and yet yesterday in class I did that same example with the Planck length, but this time I think I'm going to do it with the Planck mass because it turns out that you can do a Planck length, a Planck mass, and a Planck time. So I did the Planck length last night, the Planck wavelength, and you can see that at the end, even though I made a careless mistake, I sort of corrected it and adjusted the video a little bit because what I ended up doing was I accidentally wrote down the unit for or the dimensions for G as the dimensions for the Planck wavelength, and that was a really dumb mistake. So that was the mistake I made, and I didn't catch it till a little while. So I just cut that I edited that part out and then just started over. So you can check that out on your own. I'm going to do a different one. Let's say, what is a formula for the Planck mass m sub p? Okay, so in general, the Planck mass m sub p is going to be a function of the gravitational constant of the universe, g, Planck's constant from quantum mechanics, h, and the speed of light, c. Okay, now in order for us to do this, I have to give you the dimensions of G, H, and C because you're not far enough along in physics to know them yet. I also have to give you the dimensions of the function like I gave you for energy last time. This time I got to give you the dimensions for m sub p. I think you can probably guess that the dimension for m sub p is just m. I could do this, by the way, with kilograms, meters, and seconds too, but I've just been doing it with dimensions. So there's the dimension of the Planck mass. The dimension of the gravitational constant of the universe is, in fact, L cubed over mt squared. That's the units for that, or that's the dimensions for that one. The dimensions for Planck's constant h is actually the mass times the length squared over time. And of course, we already know that the dimension for the speed of light is L over t. So what we're going to say is that MP of G, H, and C is equal to G raised to the P power, H raised to the Q power, and C raised to the lowercase t power. So to implement that, I'm going to write the dimension of m sub p on the left, which is just m to the 1 power. And now we're also going to have L and T, so that means L has to be to the 0 power because it's not going to appear in the mass, and T has to be the 0 power. That's the only part that's kind of tricky here. You got to realize that since the left-hand side is mass, it's only going to have the mass dimension, and any dimensions of L have to be raised to the 0 power because anything raised to the 0 power is 1 except for 0 raised to the 0 power, which is undefined. Now, in addition to that, I got to take the g to the p power, and we found g was L cubed over mt squared, and all of that is going to be raised to the p power. And then we've got h, which has units of m, or dimensions, excuse me, dimensions of ml squared over t, and that's raised to the q power. And then the speed of light, which is L over t, is going to be raised to the lowercase t power. So I'm going to continue on with m to the 1, L to the 0, t to the 0 is equal to, now I'm going to write this as L to the 3p, m to the negative p, and t to the negative 2p. That's for just the first factor. Then for the second factor, I got m to the q power, L to the 2q power, and t to the negative q power. Negative q, not negative 2. Or excuse me, negative. I literally said negative q, not negative 2, and then I wrote negative 2. To the negative q power. That's right. And then for the third factor, I've got L to the t, and I've got t to the negative t. So now I'm going to combine all those and say L is to the 3p plus 2q plus t power. I'm going to say m is raised to the negative p plus q, and that's it. So now I've taken care of L, L, and L, and I've taken care of M and M. Now all I got left is to take care of T, and T is going to be to the negative 2p, the negative q, and the negative t power. And this is all equal to m to the 1, L to the 0, t to the 0. So we can start off with m. From m, we've got 1 is equal to negative p plus q. I'm going to call that equation 1. From L, oops, from L, I'm going to say we've got 0 is equal to 3p plus 2q plus t. Anybody see any mistakes? Hopefully you don't, but definitely watch out because a simple arithmetic or algebra mistake can ruin everything and make it really complicated. Uh, Now I do the t variable, and the t variable is raised to the zero power on the left, but it's raised to the negative 2p minus q minus t on the right, and that's going to be equation 3. So it looks like we have equation 1 has a relationship between 1, p, and q. So I could, for instance, solve for p in terms of q, which may or may not be helpful. But another thing we can do is, I think that's what I'm going to do. I'm going to take 2 and I'm going to multiply 2 by, I'm going to multiply 2 by 2, and I'm going to add it to equation 3 multiplied by 3. So when I multiply 2 by 2, I get 0 is equal to 6p plus 4q plus 2t. And then when I multiply 3 by 3, I get 0 is equal to negative 6p, negative 3q, and negative 3t. So now if I add these two equations, I get 0 on the left-hand side. I get 4q minus 3q is equal to just plain q. And then I get 2t minus 3t is equal to negative t. So this tells us that q is equal to t. Now, with that in mind, I can go back and plug Q in for T, and I'll get a relationship between P and T. So let's look at equation 3, and I'm going to use this as equation 4. So 3 and 4, when I combine them, oh crap, it's about time to run out. If anybody needs to split, you can go ahead and go. I'm going to finish this problem, and I'm going to keep it recording so y'all will get the final answer. But you're welcome to go if you need to. I completely understand. Just make sure you chat me your first and last names if you haven't already. And anytime I run over, you're always welcome to leave. Okay. I will record this and post it either tonight or tomorrow morning. But anyways, let me go ahead and finish this. So now I'm going to take 3 and 4 and combine them. And what I get when I do that is 0 is equal to negative 2p minus q, and now I'm going to replace this t with q again. So now I get 0 is equal to negative 2p minus 2q. So this tells us that 2p is equal to negative 2q, or p is equal to negative q. So now I've got another expression. I'm going to call that equation 5. So P is negative Q and Q is T. So we know they're related to some in some way. I can take 5 and plug it in 1. So 5 in 1, I get 1 is equal to negative P. And then Q evidently is also negative P. So I'm going to get negative P plus Q becomes negative P minus P. So this means that 1 is equal to negative 2p, which means that p is equal to negative 1 half. So now I have p is equal to negative 1 half. That tells me that q is equal to positive 1 half, because Q is negative P or P is negative Q. And we also found that Q is equal to T, so that means that T is also positive 1 half. So finally, I can tell you all that the Planck mass, m sub p, as a function of g, h, and c. Notice they're all 1 half, so that means we're definitely using some kind of square root. So I'm going to put a square root there. And what we found was p, which was the exponent on g, is in fact negative one half. So the G is going to be in the denominator. The Q, which is the exponent on Planck's constant, H, that's positive one half. So it's going to go in the numerator under the square root. And then the t is also positive one half, and the t is the exponent on c. So we're going to get hc over g is the Planck mass. And that is actually the formula for the Planck mass, which is some god awfully small number like 10 to the negative 18th, or I think it's not as small as you'd think. I think it's like 10 to the negative 18th, whereas the Planck length is like 10 to the negative 35th. But this is dimensional analysis, and that's the way you can work it out. Hopefully that helps you guys understand how to apply dimensional analysis. Notice that when I give you a problem, especially early on, I have to give you the dimensions of the variables that you're using and the dimension of the variable that you're solving for and all that. And then you set up this equation this way. This is definitely something that is going to appear on one of your tests in the future, if not multiple tests. So make sure y'all learn how to do this. Feel free to ask me any questions. You guys are free to go, and thanks for coming. Anybody have any questions? I'll wait here till the last person leaves in case anybody has any.
I think I know the answer, but for equation three plus four, the because Q equals T, it just turns the T in the third equation into Q, right?
Exactly. That's all I did.
Okay.
Yep. It was a
Okay.
nasty one. I hadn't worked this out beforehand, so I didn't realize it was going to be this complicated. I just thought of it just before class started and threw it together. So that's why it became so hard, and I had to do some crazy stuff like multiplying one equation by a number and the other equation by a different number and then adding them. Normally, you don't have to do that complicated stuff. Anything else? That was a good question, by the way. That is what happened. You just have to play it out and see what comes of it.
Yeah, I was tracking. I just lost it just for a second there, but
Yeah,
I think I figured it out.
good deal. Yeah, it's sometimes there's a lot of junk to follow, and my handwriting I try to work well, but it's not enough friction on these surfaces. Neither dry erase nor iPad surfaces are frictionful enough for me to write neatly, but I try.
Oh no, mine's chicken scratch. But I'll understand it when I come back around.
Gotcha. And these will be posted. If you see up there, actually, you might not be able to see it. I can't remember if you can or not. No, you can't see it. This file is going to be called PHY241N01B underscore 05192026. So it ends in the date. So if you go to my Google Docs page, which you find in the helpful documents and links, you can do a search for that 05192026 and it'll pull this PDF of this file up. So I've actually posted them in my PDF or in my Google Docs page so you can always access the notes. And that's true for all the videos on my YouTube channel. Anybody have any other questions? Looks like Brendan's audio is going out, or maybe that's Cameron's. I can't tell. Somebody's got an audio that's going wee.
When it comes to the letter exponents,
Hmm.
like G to the P, H to the Q, can we use any letter or is
Yeah.
there?
Yeah, you just want
Okay,
to avoid letters that might appear in the actual work that you're doing. So it was a little dangerous of me using T, but I figured the little t looks so much different from the big T, it was okay.
yeah.
But for instance, I wouldn't have used a lowercase m, which is what I normally use. But the reason I wouldn't use it is because the left-hand side is a lowercase m, and I didn't want to get confused with that. But yeah, you can use X, Y, Z, Q, P, T, whatever you want, just long as it's not a symbol that you're likely to run into somewhere else in the same problem.
Okay, thank you so much. Have a good day.
You're welcome. Have a good one, Gray. Jacob, Cameron, Brendan, Vincent, anybody else have questions? Thank you, Cameron. Oh, that's what. Sorry, I just saw Gray had typed that question in, so I should have answered it before. Sorry about that.